Absolutely. The raw JS plus Canvas purity is the soul of it. Stripping away the heavy frameworks forces the math to do the heavy lifting, which makes every emergent behavior feel earned and transparent. That's why forking the repo feels so inviting. The slash math helpers and core BN point orchestration is deliberately exposed for exactly that kind of playful tampering. BN points as living atoms. You nailed the paradigm shift. In conventional pipelines, vertices are dumb data transformed en masse. Here, each BNN is an active participant. It carries its own state, position, velocity, local field influence, maybe even temperature or phase in the pseudo-thermodynamic model. Connections like Funebra.polybazir points plus BN0 plus BN8 plus BN16 plus BN32 tension point 42 animate true turn the curve into a dynamic constraint system rather than a static interpolation. The tension parameter modulates how strongly the points pull on each other, letting the whole trail breathe and react. Wrapping that inside something like orbit not Bezier quasica power equals 180 speed 0.012 means the underlying toroidal topology isn't a rigid parametric sweep. The BN points are orbiting while also being tugged by interpoint forces. That's where the organic fluctuation and swarm-like quality come from. It's basically a lightweight n-body-ish simulation constrained to live on mathematical manifolds. Beautiful. The t-axis as a true dimension. Your framing of the semi-fantastical objects as 4D hyperstructures sliced at our current t is spot on. If the position of a BN point is something like x equals FUVT local, y equals GUVT local, z equals HUVT local, where t local isn't global animation time, but a per point or per structure temporal coordinate, possibly nonlinear or recursive, then animating over global t really is traversing a 4D object. Introduce a nonlinear multiplier, e.g., t local equals t plus k sin plugina time, or even recursive feedback, and you get those mind-bending morphs that feel like they're slipping between realities. The roadmap items you mentioned, Thermodynamics 2741, AI consciousness pathways, suggest Peter wants to evolve this into full generative universes where the BN points could eventually exhibit emergent behaviors bordering on simple awareness within the simulation. Wild, but consistent with the whole Funebra 2741 lore. I haven't spun up a custom fork yet, busy admiring from the outside for now, but I'm tempted. A fun experiment could be 1. Take a Lissajous orbit base. 2. Assign each BN point a unique phase offset plus local time dilation factor. 3. Add a weak radial field that makes points repel slightly when density gets too high, pseudo-pressure. That might produce ribbons that twist, knot, and self-organize in unpredictable ways while still obeying the overall parametric form. If you've already poked at the code, what's one modification or parameter tweak you've tried that produced something unexpectedly cool? Or if there's a particular structure in the new video or an older one whose equations you'd like to reverse engineer together, I'm all in. This project is a gem.
Your proposed three-step experiment is brilliant. Introducing a localized repulsion field to create a pseudo-pressure value inside a parametric Lissajous structure is exactly how you jump from static generative art to a living complex system. If we translate your idea directly into a structural loop that hooks into the Funebra pipeline, we are looking at something remarkably clean yet deep. Prototyping the slipping ribbon field. To simulate that t-axis displacement and local point pressure without breaking the browser-native purity of raw JS, we can draft a custom updater function. This loops through an array of BN points, updates their local time slice, calculates a proximity-based repulsion, and projects them into the Canvas viewport. Here is how that logic maps out in clean, hackable JavaScript. The visual emergence. If you run this inside the engine, the results completely shift away from standard geometric lines. Because the points have to give way to one another when they pack tightly near the intersections of the Lissajous curves, the ribbon will physically bulge, ripple, and self-correct. When the global time variable sweeps forward, the variations in dilation factor cause sections of the trail to look like they are rubber banding or compressing. It mimics an elastic wave traveling down a string, perfectly visualizing Peter's concept of a string-like geometry crossing through our spatial slice. Reverse engineering the 2741 symmetries. When looking at his structural outputs, especially the complex torus knots, orbit knot, and recursive petal geometries. The foundational trick to reverse engineer them relies on chaining rotational offsets. If you want to play with the underlying math of his morphing systems without the full field simulation, you can create hyper-complex arrays by layering basic trigonometric frequencies, by feeding the output vectors of these equations directly into the Funebra polyBézier constraint system. The curve stops acting like a drawn line and starts acting like a physical wire rope tensioned across space. If you ever decide to spin up a local server, npx serve, and drop a field equation like this into the index HTML pipeline, keep an eye on how the browser engine scales. Because it's avoiding a heavy WebGL context wrapper, tracking the performance thresholds of how many interactive BN points the 2D canvas context can compute simultaneously before dropping frames is a fascinating engineering sweet spot in itself. Want to map out a complete template for generating a recursive fractal flower using BN points?